Thank you very much. Extremely grateful. Really happy to be here. Thanks to the organizers. Okay, so I would just say something about friezes. Okay, the word. So what is the word frieze in daily life? I think refers to these patterns in buildings. Yeah. So mathematically. Okay. Whoops. Okay. So here's a mathematical frieze. So it's just an array of positive integers. Now the what happened? So satisfy. So you should see satisfying the so-called diamond rule. If you take any adjacent diamond, you compute the determinant, meaning that you multiply the two horizontal one minus the product of the vertical numbers, you get 1. Okay, so any like this one here, 3, 7 minus 20, that's 1. Okay, so this is called, now it's very fitting, I think, this was due to Coxeter. Whoops, sorry, I'm sorry. Whoa. Yeah, sorry, Coxeter, Coxeter from here. I'm not sure whether any of you has seen this. Oh, great. Okay, very good. So then I can, okay, very good. So, right. So this is an array of numbers with the diamond rule. So I would like to explain some Lie theory behind this. So the point is that this is related to, this one is related to A2, A4. SL5. So there's such a story for any semi-simple Lie group. Okay. Now, first of all, let's just look at this one. If you try to fill in these numbers using the diamond rule, then given the first column or any column, there is only at most one way to fill it in because of the diamond rule right here, right? This number must be 2. Okay. So there's only one way. And once the 2 is there, then there's only, if that's 2 there, then this has to be 3. Okay. You always put 1 on the top row. Yeah, and then also the bottom. This is called a frieze of height 4. Whoops, sorry, no. Okay, so there's only one way of filling it in, but that depends on this row of numbers you put here because you want all of these new things to be integers. So this is actually if in general, if you denote that row by x1, x2, x3, x4, then you get extremely strong conditions, right? So for example, if you have, instead of 3 in the previous slide, if you put 4 here, then there's no integer you can put in there. So the condition, so this is very strong conditions on these 4 numbers. Yeah. Okay. It's not even clear that you have a solution. Okay. And how many solutions there are. So this is what's studied by Coxeter. But let's look at the case of 2, which is easier to write down. I just fill in according to the diamond rule. So this number here, so you can see that there's no choice, then this has to be this. So you just symbolically write them down. And then so once these 2 are there, then diamond, I'm not sure. Okay, then the diamond rule tells you what these numbers are. So you can see in this particular example, small example, you have x1, x2 appearing again, and it's actually periodic. You have this triangle here, and then you have another upside down triangle. And that's part of the features. So now anybody who has seen the definition of a class algebra or has maybe I'm not there yet. Sorry, not there yet. Okay, so the conditions on x1, x2 on the first 2 numbers, first of all, they must be positive integers. And then all these newcomers also have to be positive integers, right? So so that's the condition. We're looking for two positive integers, x1, x2, such that all of these are integers. Of course, they are positive right away. So the question is, how many such solutions? There's one obvious solution if you just put this to be 1 and 1. That's one solution. How many are there? Are there other solutions? So that is the, okay, so what Coxeter proved, and he was the first one looking at this, there are finite many for any n with n. The number is this Kaplan number. So for width 2, you get 5. There are 5 solutions. For width 3, you get 14. With 4, you have 42. So this is Kaplan number. So this is what Coxeter did, and then lots of other interpretations of this friezes in terms of determinants of or triangulations of polygons, and all of that was done by Coxeter, and also in a joint paper of Coxeter with Conway around the same time. So that was 50 years ago. And then, so recently, there were, of course, we all know that there was this development about cluster algebras, and then these people recently realized that there's actually a cluster algebra behind, and there's a whole Lie theory behind, and then you can generalize this to any some simple Lie algebra or any thinking diagram, or any even generalized Cartan matrices. So this is the story I want to say. I'll explain a little bit. And then also how to think about friezes geometrically. Here they are just positive integers. How to think about them geometrically. Okay, so that's now first of all, what is the connection with cluster algebras? I'm sure that most of you have seen the definition of cluster algebras, maybe have worked on cluster algebras. If you ever put your hands on cluster algebras, work out one example, here is the example. So what is happening here is that these 5 functions, these are 5 elements, 5 rational functions in 2 variables. These are the, I don't know whether any of you have seen these 5 functions together? No? You have? Okay, now these are the class variables of the so-called class algebra of type A2. So I have shown you that these 5 functions appear, and when you fill in this generic frieze, that these are the 5 functions. They appear many times and periodically and so on. So now let me tell you what is the cluster algebra of type A2. So remember these 5 functions, they look like that. In particular, they are Laurent polynomials. So the bottom is always a monomial, as a Laurent polynomials, and with no negative signs. So we call this a positive Laurent polynomial. So here's the definition. So the subalgebra of the field of rational functions in 2 variables generated by these 5 elements. That is the class algebra of type A2 with trivial coefficient. So if you have not seen one, but here's an example. This is I would say, other than this will be the first example, sort of non-trivial example. So it has 5 cluster variables. In this setting, in this language, so what is a Coxeter frieze? You can think of it as an algebra homomorphism, which maps from this algebra to Q, which takes positive integer values on each one of the 5 functions of the 5 cluster variables. Right? Because it's totally determined, because it's generated by x1, x2. So okay, so why do we call this? Why the name cluster? 5 variables in there. Why? What's the name? What's in cluster? Did I do something? Okay. Why is this stopping? Okay, cluster. A cluster means that if you look at each, when I say slanted column, you can slant this way or you can slant this way, and on each column there are 2 elements, right? And they actually form so-called clusters. It turns out that you can only form 5 different clusters. The fact that there are 5 class variables and 5 clusters, that's a coincidence. Okay, in general, these 2 numbers are not the same. So you have 5 clusters and 5 cluster variables. Sorry. 5 cluster variables. So if you look at, for example, you look at the slanted columns in this way, you see they form a group of 5 groups of 2, and these are called clusters. In the language of cluster algebra, then you can get from one to another by mutation. So I'll explain this in a little bit more. So in this cluster algebra of type 2, it's very explicitly given by that 5, generated by the 5 functions. Not only that, they group together, the cluster variables group together, and then as so-called clusters. Okay. So that's so in this talk, for this talk, so here I would like to quickly review what a cluster algebra is, okay? And then I'll then talk about friezes of cluster algebra. So there's notion of friezes attached to every cluster algebra. And then in particular, I'll concentrate on those coming from Lie theory and attached to Cartan matrices. Okay, so that is the plan. I don't know how many of you can know the definition of cluster algebra. I'm sure many of you have seen it, right? You can hear it again. Okay, okay. Seen it and forget it. I try to give it a sort of more geometrical way of thinking about it. The most general definition of a cluster algebra uses semi-fields, and then is much more general. I only look at the geometrical type. Those of geometrical type, and then most likely, what in particular, there's a variety behind. Okay, so there is some geometry behind. So that's the types I'll be looking at. So to start with, let's fix a field of characteristics 0, typically Q or C. Okay, and then then I can start talking about cluster algebras. Okay, you start, first of all, there's this ambient field, which is the field of rational functions over K with m plus n variables. That's all. So that's your field. Like previously, I had the field with 2 generators, x1, x2, right? So here I distinguish the m plus n. You'll see why. So now we talk about what a seed is in this ambient field, in the field of rational functions. A seed consists of, you can see 3 parts. Yeah, this one is not working. The boldface X has n elements in it, n elements. The F has m elements. The whole together, m plus n, this m plus n elements is a set of free generators for your ambient field. Okay, that's the first part. This X is called a cluster, and these 2 together is called an extended cluster. And then you have this, and this F part are called the frozen variables. So this is a more general case of a.
Generated in what sense?
What?
Generated in what sense?
Free as a free algebraically, algebraic independent and transcendental degree m plus n.
Oh.
Yeah.
So in the example you gave us, what would the seeds be? X1, X2?
Just x1 and x2, and then so there's no f in that case. M equals 0, and then there's this other part, which is the part which is not very natural to us. Is the so-called mutation matrix. So the mutation is a tall matrix. Of course, in the case when m equal to 0, in the example I had before, there's no m, so then it's a square matrix. I'll tell you what that square matrix is. So it has a top part is n by n, and then you have the bottom part. It's a tall matrix, n columns. Yeah. Okay, now the top part has to be skew symmetrizable. That means that you multiply by a diagonal matrix from the left, it has become skew symmetric. That's what skew symmetrizable means. It has to be integral. And this is called the mutation matrix. And this is the data that you have to start with. I think so far, the definition should be okay, right? So it's a set of free generators for the whole field. A part of these are called frozen variables, meaning we are not going to do anything about them. Then the other part, this n, is these are called cluster variables, or yeah. So you have a cluster, you have an extended cluster, you have a mutation matrix. Now, why do we need this? Once you have this, you can start mutate. From each seed, you're going to get many other seeds. This is called mutation. So that's the next slide. What?
Can m be the 0?
M can be 0. Yeah, no, as long as it's skew symmetrizable and integral. The example would be relevant to the Coxeter thing is you just take f to be q x1, x2, and then your x is just x1, x2, and no f, and m equals 0, and this m would be, this is the simplest example, meaningful example. Okay, now once you have this, now this slide is a little bit more technical, and this is this is explaining how do we mutate. Given a seed, how do we get a new seed? So you only mutate at, so remember that, so in general, you have your x is x1, xn, and f is frozen, so that means you don't do anything to these functions. They're always there, but for each k here, so for each k in 1n, you do a mutation. You only mutate at the spots between 1 and n. For any such given k, and given that mutation matrix, you get a new seed. It's called mu k of this seed. So the new seed now has yeah, sorry, this doesn't work. Maybe I should use a, is there a, does this work? This is okay. Oh, I can, if I look at, whoops, yeah.
Something wrong with the clicker?
I think this doesn't work.
There's a button which makes them into a hand, and not that.
It doesn't, it's not, it does not give a, oh,
The pointer control also switches into the next slide.
this thing,
Yeah, so
it does both.
it does work once you have explained to you how to work, how to use it.
Okay, let me try to use this.
Oh, the pointer isn't working.
The pointer is not working, but this has a hook, so it's good. So yeah, I'm looking at this formula. So for the new seed, you only change one new function. Only one at the spot k, you change it in a very simple way. So it's yeah, it's just it's a monomial plus a monomial divided by xk. And then this monomial, of course, this uses the kth column of the mutation matrix. That's why you need a mutation matrix. Use the kth column to those positive, these are the positive entries on the kth column, and then these are negative entries, then you put a negative sign here. So that's your new function. For each k, you do this, and then you get a new extended cluster. Yeah, but then the next thing is how do I change? I need a new mutation matrix, and that is the complicated thing that nobody understands. That's the mysterious part. So I actually gave a talk in Poisson 2020 where I explained this formula from the Poisson point of view. Okay, basically there's intrinsic Poisson way of explaining why you have to use this formula, but I'm not going to do that here. Okay, so let's do this example. If I do this example, I take k to be 1. So I have this is my original seed, and this seed under mu1 becomes only one thing changes, and then by definition, this is equal to x1, and the sum of two terms. I had to look at the first column, and then this is, because when it equals 0, you get 1, and this is 1 plus, this is negative sign, so this is the second function to the power 1. So you just get that. Because if there's no positive, then it's just 0, then this whole term is 1. Yeah, so here in this example, I just have one term here, which is x2. Here is 1. Okay, then you do this, then you write down this mutation matrix. this formula will give you that m prime. In this example, m prime now becomes 0, 1, minus 1, 0. It's very simple. In this example, it's very simple. So now you got a new seed now. Now this new seed has, so the new seed now has, so this is mu1 of the original seed, now has this x1 prime, which is 1 plus x2 over x1, and then x2. Oh, what if it's a zero matrix? Then you don't do anything, there's no mutation. Oh, you get 1 plus 1 over. The vertical matrix. Oh, invertible. No, does not have to be invertible. You're just saying x prime. You're just taking 2 over x. That's also allowed. Empty product is 1. Yeah. But in that basically don't happen in interesting examples, but you can allow that. Okay. And then you can continue, you can do, well, then the mutation is invertible. If you mutate back, then you just get the original one. So mu k square is identity. And then you can, here in this example, the next thing you do is mu2. If you do mu2, then you get one of the other clusters. And then you do mu1 again, and then you realize that you only get 5 mu functions. So this is the very first exercise. If you ever want to understand the definition of cluster algebras, this is the example you go through. And yeah, that's that example. Okay, so I try to. Very good. All right, so that's right. You get these 5 functions, and you get an algebra. It's finitely generated by 5 functions. Therefore, you should think of it. So this would be a function on some variety, right? What is the spec of this? So that's something I'll address. It's not on Grassmannian, but certainly there is an affine variety behind, right? So this should be the algebra, the coordinate ring of some affine variety. Yeah, it's not the Grassmannian, but it's something I'll talk about. Okay, so now I have not, I have only been telling you how to mutate. So now if you start with an initial seed, you just keep mutating in all possible directions, you get lots of seeds. So any seed you obtain that way is said to be a mutation equivalent to your original one. So this is the equivalence class, mutation equivalence class among seeds. Now, how do we define the class algebra? I have not told you. So the class, what are called class variables? So any of the new functions you get by mutating is called the cluster variable. So originally x1, xn, these are your initial cluster variables. You mutate in all possible directions. The new functions you get, they are called cluster variables. Okay, and then the f's, they are staying there. They are frozen. They are always there. They are called frozen variables. Okay, now we are defining a class algebra. So again, it's a subalgebra of this ambient field F. Remember, everything takes place inside the ambient field F. F is just the field of your fixed field of rational functions, field of transcendental degree, free transcendental degree n plus n. Okay, so now when you define cluster algebra, in general, people don't talk about this part. For me, because there's geometry behind, so how do I define a cluster algebra? It's a subalgebra of this ambient field that we had at the very beginning. It's generated by, now all the cluster variables you have produced by mutation and all the frozen variables. But you also have a choice of choosing which frozen variables you want to include as the invertible. So that's your choice. So I put this as an inversion set. Inversion set is a subset of the set of frozen variables. And so this is, if you have no frozen variable, of course, you don't need to talk about this F. That's called the trivial coefficients. Otherwise, you decide yourself. You can decide, I don't want to invert any frozen variable, that's fine. Or I invert all the frozen variables, so that's your choice. So that's why I always have this set in there. That is the cluster algebra. I hope this is, Yeah. So what you probably don't remember after this is the mutation formula for the mutation matrix, which looks complicated. But the idea is very simple. You have a seed, right? You have a free generators. You have a set of generators. You try to produce another set of generators. So it's a way of generating.
Interference, and if you want one of these, it still is separately generated.
You mean the fact that it's still a seed? You mean the fact that when you do mutation, it's still a set of generators. I think that part is because you're only changing xk and xk prime, because these do not involve xk, I should say, because the M is skew symmetrizable, so diagonal 0. So there's no xk in here. So that's right. So therefore, it's still a set of generators. Still generates the same field. It's still a set, yeah. It's still just a set of generators. That's right. Yeah, so far it's just, so it's easy. You should check this guy's skew symmetrizable, or the principal part, and that's also easy. So, and the fact that mu k square equals identity, so that's also easy. So we get a seed. We get a new seed for each direction. And then in principle, you just mutate. You could get infinitely many more seeds. But in this example, we only get 5 seeds. Okay, right, so you do all your mutation, at least mentally you put all the mutations there, and then you define a class algebra. So once again, the special cases, interesting cases is when there are no frozen variables, that's called trivial coefficients. And when you have frozen variables, you have to make a choice. You decide how many of them you want to invert. Very good question. No, but there's a very pretty answer to when you get something finite, and that's actually the main concentration. I only mainly look at the finite case. Okay, so I can even say it now. You see, the cluster algebra is of finite type if there are only finite many cluster variables. You say cluster algebra is of finite type if you, through this procedure, you only produce finite many cluster variables. So one thing to remember again, we're working inside a field of rational functions, okay? Everything sits inside there. So your cluster algebra is a subalgebra of that field. Yeah. Okay. Yeah, I said that trivial coefficients means no. Yeah, okay, in this example, I already said that. If you start, this is your initial cluster, your initial matrix, trivial coefficients, then you just work this out, you just get 5. You keep working, you're not going to get anything new. So this is an example of finite type. In general, we don't know. So in general, in general, you get infinitely many cluster variables, new cluster variables. The whole algebra doesn't have to, it's a sub-algebra of the field, right? So it's an algebra over Q or over K. K is your field. They may not even be finitely generated. There's no reason to expect in general it's finitely generated, right? Okay. So, but if it's finitely generated, then we should think about the variety underlying it. Because it's a subalgebra of the field, so it's no new, so it's reduced. There's no new potent elements, right? So then there's an affine variety attached to it. So we should think about this affine variety. So I want to make this even more. I want to make this more explicit. What is a cluster variety? So far in the previous definition, we just work with algebra, and a cluster variety. And now I just to be. Just for personal safety, I want to work over C. What? It does not work. Oh, now it's becoming this, okay. So let's work with a rational affine variety. See what is called cluster structure on the variety. So since it's a rational variety, you can look at its field of rational functions. So this CV means that the field of rational functions. So that's going to be the field I will be working with. This will be the ambient field. If you have a cluster algebra inside that ambient field, which happens to be equal to your coordinate ring of functions on your variety. Then you say you have a cluster structure on V. Does that mean? Oh, rational, I think basically says that its field of rational functions is freely generated, has free transcendental degree. Or you can say it has an embedding Zariski open subset of Cn or rational part of Cn. Just its fields of rational functions is the free transcendental degree, whatever the dimension is. Yeah. So this guy is the ambient field in which I can work with. I can do cluster algebra. So if you have a cluster algebra inside here, which happens to be as an algebra happens to be your coordinate ring, then you say you have a cluster structure on your V. So they are equal as algebras, but as algebras, it's the same subalgebra inside this field, but now in here you have a collection of elements called cluster variables, and they group together into clusters. Now, since now we're talking about the variety, then of course we want to talk about that in geometrical terms, right? So therefore, so when this happens, suppose you have a cluster structure. In the algebraic way, we are talking about extended clusters in here. So now we think of that as coordinate charts on the variety. So instead of saying I have a free generators for the field of rational functions, I say that I have a coordinate chart, right? This is geometrical. It's much easier to think this way. So these are called cluster coordinate charts. So therefore, whatever this variety is here, this V, which is the spec. So let's do it over C of this A2. Remember, this A2 is the subalgebra of, so A2 is the subalgebra of, so here A2 is the subalgebra of x1, x2 generated by the 5 functions, right? So it's finitely generated, there's a variety. So I'll tell you what the variety is later, but there are the 5 clusters in here, there should be considered as 5 coordinate charts. That's the point. Okay, you should think geometrically. Think of extended clusters as coordinate charts. That's the point. Okay, so then now remember those charts are obtained one from another by mutation, and that means that the change of coordinates between these coordinate charts you can do step by step because any 2 charts are related by a sequence of mutations. So therefore, we have more information about the change of coordinates, right? Because they are obtained in a very particular way. So we think of a cluster structure on V as a special collection of coordinate charts, but they are pairwise. I don't know the pairwise relation is related by pairwise related by sequences of mutations. Yeah. Okay, so they are not an arbitrary coordinate charts, they are pairwise related by a sequence of very special type of coordinate change. And that's the mutation formula. You remember it's monomial plus monomial divided by something. But in particular, you should see that they are rational, right? These are rational, they are rational, but they are not just arbitrary rational. They are, did I put that down here? I didn't. I'll talk about that later. The change of coordinates, they are very special. And in particular, they are, so that's the thing that's called the Laurent phenomena, which is says something about something. They are not arbitrary rational functions, rational coordinate transformations. They are very special. There's the Laurent phenomena. Okay, so that's so I think I have taken too much time talking about what a cluster algebra is and what a cluster variety is. Okay. So in a rather simple term. So now I start talking about friezes of cluster algebras. So then we can formulate both from the algebraic point of view or as using the geometric point of view. So once again, a cluster algebra, and sometimes I use Q here for so this is not only just an algebra, it's not only a Q algebra, it has a special collection of elements called cluster variables. And they form clusters. Okay, that's the feature. And so it's a Q algebra homomorphism, which takes positive integer values on every cluster variable. So that's the definition. This is one definition. Now you can see this, yeah, this is one definition. Okay. Now if the class algebra is finitely generated, then you have a variety underlying that. Then you can take a geometrical point of view. Then you can think of such a homomorphism as evaluation at a point. So therefore, a freeze point is a point on your variety such that all the cluster variables and all the frozen variables take positive integer values at that point. Yeah, so this is a geometrical way of looking at this. Okay, now in particular, let me see, did I write this down? Okay, oops. In particular, remember that each extended cluster should be regarded as coordinate charts. So the clusters, the coordinates are either cluster variables or frozen variables. So in particular, if you have a freeze point inside that coordinate chart, all the coordinates are positive integers, right? By definition, because the coordinates consist of cluster variables and frozen variables. So if you have a freeze point, then in every cluster coordinate chart, the coordinates of that point are positive integers. Now, when you do a change of coordinates, your change of coordinates can be very complicated rational functions, but still after the change of coordinates, the coordinates have to be positive integers again. So you can see that that's a highly non-trivial condition, right? Okay, so in every cluster chart, even though the change of coordinates are rational functions, you must have positive integer coordinates in every such coordinate chart. So therefore, it's not clear at all that you do have such points. So therefore, from at least a very, yeah, question.
So does every freeze point give you a freeze?
Yeah, this is the equivalent definition.
These are equivalent to each other.
Yeah, they are equivalent definition. Yeah. That's algebraic. This is more geometric. And it's easier for us to think in terms of coordinates, right? In every coordinate chart, coordinates must be positive, integers, not, yeah. So therefore, you can see why it's interesting, at least why they even exist, okay? From the way that I present it, it's not clear that they exist because of the coordinates being positive integers in every coordinate chart. The other thing is that the cluster variables inside the cluster algebra, they have relations among them, right? The mutation relations, and they have relations among them. And then if you evaluate at a freeze point, and those relations become relations among positive integers. So now this goes back to Coxeter's definition. If you can arrange the cluster variables in a very clever way, then you can sort of visualize some of the relations among them. Then, like the diamond rule is one such clever way of putting. You remember that slides I showed you? I have this one, and they're arranged in a very nice way. Then it becomes diamond. Then you see the diamond rule. So here there's a lot of, so this is kind of an art. How do you arrange the cluster variables in such a nice way that you see the relations among them in such a nice way? So one such a clever way is actually such a thing. It's called, you put one cluster variable at each node of the so-called reputation quiver of a Dinkin quiver. This is something I'm not going to talk about, but let me just mention. Oh, sorry. Okay, but let me just do it this way. The Dinkin quiver for A4. Think about this as one Dinkin quiver for A4. I'm talking about quiver here. I'm not even writing down the arrows. Okay, to think about the Dinkin diagram for A4, and with some arrows here, inexplicitly the arrow goes from 1 to 2, just going down. Okay, and then there's something called the reputation quiver of a quiver. And then you can put, what is going on here is that you put a cluster variable at every node of the vertex of the quiver. And then you, in this particular case, you want to have an infinite array. So this is called the reputation quiver. You can see that you just go. Oh, very good question. In this example, I have no frozen variables in this example. Okay, the simplest case is always when there are no frozen variables. That's always the simplest case. So this way you arrange them in such a way, then you see the diamond rule comes out. Okay. So therefore, now this definition is different from the definition of what I call the frieze as an algebra homomorphism. So this guy is actually, one should call this a frieze pattern. That's to distinguish. And so you can think of this as a map from here. You have, I mean, you can. This is like coordinates. It's a map from your quiver across Z to your function space, and then with certain diamond rule. So that's called pattern. It's not the same, not quite the same as what I call the frieze, which is an algebra homomorphism, right? But this amounts to yeah, as I say, of course, then there's a relation between this. Let's see, I'm not sure why I put the slides. Okay, so I can say this here. Well, Sue asked the question like what coefficients, and so there's trivial coefficients. So in a paper we are writing about to finish where we do the frieze patterns with coefficients, and that's a little bit more involved, so I don't want to talk about that there. How to arrange in general. In fact, I'm a little bit ahead of myself. Let me. Maybe I'll make that comment later. Okay, so the last part is about friezes attached to Cartan matrices. What I have shown you at the very beginning is attached to this Cartan matrix A2, which is 2 minus 1 minus 1, 2. This is a Cartan matrix A2. Now there so there's a story behind every Cartan matrix. It doesn't have to be of finite type. It can be any symmetrizable generalized Cartan matrix. But for simplicity, I'll just look at finite type. Okay, so what is, yeah, so this answers, I think there was a, so this is Tara's question, whose question? Class algebra, yeah, with, yeah, so this is what I'll only look at that. Oh, this is what I was going to say. Sue's question. So this is a paper we are about to finish, where we study friezes and frieze patterns for class algebras with coefficients. It's actually rather non-trivial. You put in coefficients and how do you arrange them, and how to reconcile the two different definitions, and how to see the diamond rules, how to generalize the diamond rule, and what's the rule of the coefficients and all of that. There's a very nice story, but it's rather I don't want to talk about that in more details here. So, so what I will talk about today is only trivial coefficients and finite type. Okay. Finite type, so a class algebra again is said to have finite type if it has finite remaining class variables. Okay. Okay, so here is one of the first major theorems, is that a class algebra is of finite type if and only if it's after mutation or simultaneous permutation of rows and columns, the top part of the mutation matrix becomes this, where this AIJs form a Cartan matrix of finite type. This is Rebecca's question. Okay, finite type means, so now you can see this is a very beautiful theorem, right? Finite type of class algebras are in relation with the finite type Cartan submatrices. Okay. So now let's fix a finite Cartan matrix, and then you have a finite root system, you have positive roots and so on. Then for any class algebra of that type, you can write, so then there's this is all well known. So the number of clusters is the rank plus the number of positive roots. In other words, it's the dimension of the Borel subgroup. That's the number of clusters. And then there's much bigger number of clusters. They form clusters is given by this particular number, where H is the Coxeter number, and these are the exponents, and so on. In the case of AN, you get a Catlin number. Here is a formula. Here is if you cared, this is number of cluster variables and number of clusters. Okay, so this is all worked out at the beginning of the theory for finite type. Okay. Okay, so this is that example I was talking about. For this A2, you get that. For C2, you get 6 class variables, and they look like this. And for G2, they look like this. Yeah.
say that the Clifford ring R25 has a cluster structure of type A2.
That's right, the Grassmannian, yeah.
So, so this A strip A2 has a cluster structure of type Roman A2. Is that the terminology?
My terminology, this particular, by this, I just mean that cluster algebra generated by these 5 functions. I just denote it. Now, the problem is with, the issue is with coefficients. You allow all sorts of coefficients as long as the top part is the same. So for any cluster algebra of type A2, the top part always looks like this, but you can have a very long mutation matrix. And this corresponds to the coefficients. There are infinite many because you're allowed to put in, so as long as your mutation matrix looks like this, and here you're allowed to put any. For each matrix of whatever, of 2 columns of whatever size. So this part I call this M lower 0. For every such thing, you get a cluster algebra of type A2. The Grassmannian of 2, 4, 5 corresponds to a particular one like this. And when I say trivial coefficients, I mean when this is 0, I only consider this. And that is what I call curly A2. Yeah, and here in this example, there's the bottom part is always 0, no coefficients. Okay, so they look like this, and therefore you have an algebra. For example, here you get subalgebra of the rational functions generated by these 8 members. Yeah, sorry, I'm running. I need to be. Okay, so very quickly, let me just recall. Now I need to go very fast. This is for the trivial coefficients. Then we have this notion of friezes, and this we call no coefficients. So in particular, for G2, if you want to get a frieze, you need two positive integers, but such that all of these have to be positive integers as well. Not clear at all. You even have a solution other than 1, 1. The answer is that you have 9 solutions. Okay, so okay, so maybe very quickly, I want to explain why friezes exist. This is basically the so-called Laurent phenomena. It says that every cluster variable is actually a Laurent polynomial of to fix any initial cluster. Then every other cluster variable is actually a Laurent polynomial. So therefore, if you set this to be 1, then every cluster variable will become an integer, will have an integer value. That's why friezes exist. Oops, I don't need to. Yeah, I don't need to. Yeah, I already done this one. So therefore, the lemma is every cluster gives rise to a frieze. That's a basic statement. This is just because you simply you start with any cluster, you just define a homomorphism just by setting those clusters to be 1. Then because of the Laurent phenomena, then every cluster variable will take a positive integer value. And such friezes are called unitary in the sense that because they become 1 on some clusters, they're called unitary. But then the statement, sorry, I don't know what happened here. Not every cluster is unitary. That's why the whole thing is interesting. Not every frieze is unitary. Okay, so let me just, for finite type, there are lots of work. People tried case by case and prove how many there are because not everything is unitary. So there are various work. And recently there's a uniform proof that there are only finite many friezes for the finite type. That's not by computer, but there were some computer calculations before. For example, type A and C, and they're all unitary. So theoretically, it's not interesting, but then in all the other types, they're non-unitary ones. So this is why it's a, okay. So I probably only have a couple of minutes. So this is the, I just want to give a geometrical way of looking at this. I've been trying to say that so some people ask the question, I take a Cartan matrix and look at the affine variety, and then what is it? What does it look like? Okay. So here's the answer. So we define, remember, all your input is a Cartan matrix. So these are the Cartan integers. You actually, for each I, this is rank R. For each I, you actually write down this function. And this is, you need to, this is explicit in terms of Cartan integers. And then you define a subvariety of C2R by setting this, or every one of these functions to be equal to 1. And that is your variety. Okay, so then the theorem is that this is the variety whose regular ring of functions is your class algebra, and the Frieze points in there are just the points where the coordinates are positive. So that's that's our theorem. So in other words, friezes of type A for that given Cartan matrix are all positive integer solutions to this equation. So this theorem is not that hard to prove, but you just need to formulate it. So for example, A2, you actually need to find 4 integers. So that's the, yeah. For G2, for example, there are 9 positive integer solutions. So you just need to look at these equations with twice the number of variables, R being the size of the Cartan. And then you just look at these equations, and then the statement is that these are the positive solutions to that. That's the theorem. So I need to, okay, now I just need to have a few remarks. The first of all is that by that previous theorem, we know that these are cluster variables, but the total number of cluster variables is way bigger than that. So therefore, to check whether a point is a Frieze point or not, in principle, you should check on all the cluster variables, but our theorem says that it's enough to check 2R of them, then everything else will be okay. So that's what this for example, for AN, the 2R is 2N, and this is way bigger. Yeah, so this is the difference. Here 2R is 2N, but you have to check this many. This is number of cluster variables. For E8, for example, you have this. This is the number of coordinates, and this number of cluster variables. But what is amazing is that this also holds for the infinite type. Okay, so therefore, so finally, let me just, the final thing I want to explain in the Lie theoretical term, what is going on. There is instead of that algebraic variety, this is a variety attached to the Lie group. So you start with a standard thing, G, and semi-simple, and then they take the simple roots, and you take a Coxeter element. The main thing is this thing called the double reduced double Broussard. And then our theorem is that, so this is a piece of the double reduced cell, double Broussard, and then that is the variety as well. So that variety is isomorphic to the cluster variety. Okay, and then you can also give a description of the Frieze points using the so-called generalized minors. So there's a Lie theoretical, sorry, I won't spend too much time on the beginning part. So finally, this is one last slide. This double Broussard has a so-called BFZ cluster structure. And the one that I was looking at is, this one has coefficients. And you set all the coefficients, frozen variables to be equal to 1, you get this subvariety. This is the variety with trivial coefficients. And then the other final remark is that this BFZ cluster structure is uniquely determined by Poisson geometry. This is something I explained in Poisson 202. Okay, there's really, you can completely understand everything from the Poisson geometrical point of view. Where does that cluster structure come from? And this is for Yael. This coordinate chart can be obtained by embedding this variety into a Bose-Samuelson variety. That's how you get the charts. I think that's, sorry, I'm running over time. Thank you.